Let's get started with lecture 11, the MCUNet Tiny Neural Network Design for Microcontrollers. This is my favorite class, where we finally have covered all the techniques we have talked about so far about inference, right? So we can use these techniques and design this tiny little neural nets that is deployable on microcontrollers. Okay, all right. So here is the agenda for today. We'll start by talking about what is TinyML, right? And understand the challenges. What are the challenges, and how do we solve the challenges by tiny neural net design? Okay, covering several applications in vision, in audio, and also time series, and also anomaly detection. Okay, let's start the journey together. What is TinyML? So this is the other direction, the big ML, right? Today's AI is just so big. For example, the OPT models we are recently working on has 170 billion parameters. Okay? We cannot fit it even in a single GPU for inference. We need 8 GPUs to just run inference for such a large model, right? So we need TinyML and green AI. So the TinyML have several advantages, right? So if we have to upload the model to the cloud, what is the drawback? Privacy, right? Your data is uploaded to the cloud, right? So people might be malicious, stealing your data, right? So instead, we want to make sure all the model is local, right? Both for inference and also for training. Okay. For example, iPhone these days will understand your photos. You can search, like going to the beach, having a party, something in your album, so understand your photos. Can we go even smaller, right? So that's TinyML, Tiny AI, right? So for these IoT devices, for these microcontrollers, we want to be AI to be everywhere, right? These IoT devices are highly accessible, super cheap, like $1 to $2, and almost everywhere in our lives. Okay, we can democratize AI to a much broader audience, to a broader outreach, right? By enabling AI on these small devices. And actually, those devices are actually quite ubiquitous, tens of billions of units every year, and it's growing pretty fast. And they are super cheap, super low cost. And also they are of low power, right? They can be powered by a battery very easily. It can last a long time in the wearable devices, in factories, etc. Okay. And also we can have such TinyML in smart home, right? You can say, okay, Google, or hey, Alexa, open the curtain, turn on the light, right? Play some music. Those are tiny speech recognition applications. And also smart manufacturing. We have this kind of anomaly detection for one-dimensional data, time series data, okay, widely used in smart manufacturing, and also those vision-based anomaly detection, right? Rather than having some engineers to eyeball check some of the anomalies, right? It'll be great to have a camera sitting over there, just improving your productivity, right? And also personalized healthcare. Imagine every person is different, right? And we want to be more accessible and easier to get the predictions and know what is our body doing, right? By having something like a watch or some other sensors that is mobile, that is portable, very small, and very accurate, right? And can tailor for everyone's individual body conditions, medical history, right? So that's personalized healthcare and wearables. And also precision agriculture, when to water the crop, and also whether classifying different crops, right? So a lot of applications as well. And lots of scenarios are underdeveloped, right? So AI is quickly getting into every domain of our lives, but not all the domains, right? Computer scientists are particularly in some domains like autonomous driving, but not everyone is doing that for the whole society, right? So TinyML is really a good tool to penetrate AI to everywhere each aspect of our lives, right? So hope that's enough motivation. So let's talk about the difficulties, right? So cloud AI, mobile AI, we can easily get gigabytes of memory, right? But for these microcontrollers, the SRAM and the flash is super limited, right? 320 kilobyte of memory for activation memory, and about 1 megabyte for storage for those weights, right? So we'll talk in detail what's the difference between this SRAM memory versus flash storage very shortly. But there are just 3 or 2 to 4 orders of magnitude of drastically smaller amount of memory resources, right? So there's no prior art about neural network design for tiny scenarios, right? So we should rethink about the design space and the design methodology for such TinyML. So for these mobile phones, right, we are sometimes constrained by latency and also energy, right? But now we have a new constraint, which is the memory constraint. For a mobile phone, we can easily get gigabytes of memory, okay? Although you want to have a particular allocated memory space for different applications, but this is a lot of memory for you to use. But here it's only a couple of hundred kilobytes, right? So this memory constraint is a new challenge for TinyML. So we want to understand the challenges deeper, right? What's exactly the difference between this SRAM versus this flash, the activation memory versus the weight memory. Okay. So let's have a recap of the CNN architectures. Okay, so there are several convolution layers followed by very few or none fully connected layers, right? So after each convolution, we have activation involved with the kernel, then we have an output activation, right? So for the kernel, the weights, okay, they are static, right? They are not. They are the same across the life cycle of inference, right? So we can put them in this read-only memory, such as flash, right? This is permanent. This is storage, right? And for input activation and also output activation for different images, those activations are different, right? So we want to put them in the both readable and also writable memory, right? So we put them in the SRAM. Okay. So for these microcontrollers like Arduino Nano, it has 256 kilobyte of SRAM, 1 megabyte of flash. Okay, so give you an idea how small, what is the range of memory resource to store the activations and store the weights. Okay, and this is another popular dev board, STM32F746, which we widely use in our experiments. Okay, and also we'll be using that for your lab 4. Okay, we give you opportunity to play with one of such boards and to implement a neural nets so we can demonstrate to your mom at home. So this board has 320 kilobytes of SRAM and 1 megabyte of flash. And all our job is to be able to squeeze the neural nets so small enough to fit such tiny little devices. So the flash storage, okay, so that's concerns about the weights, okay, the model size. Since the model weights are not changed, so they can be put in the static read-only memory. Okay, so we need to hold the weights unchanged across the entire life cycle for this IoT device. And the other side is the SRAM. Okay, SRAM is even smaller, a couple of hundred kilobytes. Okay, so we store these input and output activations, okay, in the SRAM, since we have to both read and write, and it's dynamic. Different inputs, different layers, the number is completely different. Okay, so we care about the peak SRAM during inference. Why peak SRAM? Since for inference, once we finish layer I, at layer I plus 1, we can throw away the activation of layer I, since we are not doing any back propagation, right? Just feed forward. So the peak memory determines the real bottleneck. As long as the largest layer's activation is smaller than 256 kilobyte, then we are okay, right? But if all the layers are like 10 kilobyte, only one layer is 257 kilobyte, then you still cannot fit, right? So we care about the peak SRAM. So here weights are not counted since we can partially fetch the weight, right? For calculating layer 1, we just need to fetch the weight for layer 1. So a good approximation, the SRAM usage is just input activation plus output activation. But in the real scenario, we also have to consider these partial weights, okay? And also for the flash storage, we also have to consider the code segment. If you have learned 644, you know that the code segment also take some of the flash, some of the storage, right? For microcontrollers, this is non-negligible. So reducing the code segment by doing such compilation-based approach, we have to be very careful about the code size of your model. Okay. A question?
So when you're running a neural network on a computer like that has an NVIDIA GPU, where are these on the computer? Are they the RAM of the computer, or are they something?
Oh, so this is just for microcontroller, right? For GPU, we have a lot of a lot more resource. For GPU and normal computer, we have the DRAM. On microcontroller, we don't have the DRAM, right? So between flash and SRAM on GPU, we have a pretty large DRAM, right? For example, the A6000 GPU that we have in our lab has 48 gigabytes of GDDR, GPU DDR. So that's the difference. But on microcontroller, there's no DRAM, there's no operating system, there's no paging. So everything you have to manage by yourself. It's called bare metal.
Is SRAM the cache on the chip itself, or what exactly? Why do we not have DRAM?
So everything is just one single chip, right? DRAM is a separate chip. Okay. So the microcontroller contains only a single chip, and that's the whole computer.
And the flash is also embedded.
That's the flash is also embedded in the chip, embedded flash.
Did you not just buy a separate SRAM module and just address that yourself? Put it on a PCB with the microcontroller?
You mean DRAM? SRAM is on the chip. You mean DRAM?
Yeah.
So that's no longer the something that's $1 to $2. Right? So you want to make it tiny, small, and low power. Yeah. All right. So let's see, what is the gap roughly like? So rather than 50, remember we talked about the real bottleneck is the peak SRAM, right? So the largest layer, right? So rather than 50, so this is the amount of peak SRAM that is required. Actually, from ResNet to MobileNet V2, the peak SRAM didn't get decreased by too much, right? Because conventional, this kind of model design are for mobile devices, MobileNet, right? On a mobile phone, you really don't care if it's like several, in the order of magnitude, several kilobytes, since the mobile phone can easily have gigabytes of memory. But for tiny microcontroller, this is not the case. Even if we quantize that to int 8, dividing this number by 4, this is still much larger than the resource constraint, the SRAM resource constraint of a microcontroller. So we want to bridge this gap. So let's see what is achieved by prior work. For example, in 2016, ResNet was proposed. 1 year, 2 years later, MobileNet V2 was proposed. At that time, people are focusing on reducing the number of parameters, right? So the number of parameters gets reduced by 4.6 times. That's actually pretty significant. And they are both having the same, like 70% ImageNet top line accuracy. ResNet 18 versus MobileNet V2 shrink it by 75%. Okay? However, what we care is also the peak activation, right? The largest layers activation. From ResNet to MobileNet, actually that didn't decrease, but I even increased, right, by 1.8 times. So anyone have some idea why? What is the, since we talk about the architecture for both ResNet and also MobileNet v2, anyone can think which layer resulted in the larger peak activation size. The inverted bottleneck, what does it look like? How many layers? What is the architecture for 3 convolutions plus activation, right? And we have a 1x1 convolution followed by 3x3 depthwise, right? But there is an expansion ratio that is either 3 or 6. What does that mean? That increased your number of channels by 6 times by using this depthwise convolution, right? So the activation also grows a lot, although that saves the number of weights because it's a depthwise convolution. The number of parameters is no longer like 3x3 by input channel by output channel, but 3x3 by output channel, right? But that saves the weights, but the 6x expansion ratio greatly increased the activation size. So that's the limitation for this MobileNet with respect to the size of activation. So we will discuss MCUNet that also reduce the number of peak activation, right? So is everyone on the same page? Why MobileNet v2 has, what is the expansion ratio? Why is 6 times larger? Yeah, I see some confusing faces, so let me repeat that. So for MobileNet v2, right? Remember the structure is a 1x1 convolution followed by a 6x expansion ratio for the channels, okay, followed by another 1x1 layer, right? So this layer is a depthwise layer, okay, depthwise 3x3 convolution. The number of channels is 6 times larger than its input. So that's the reason this inverted bottleneck. So bottleneck is like this, right? So this is bottleneck. You have 1x1, here 3x3 in the middle, and 1x1 in the end. This is bottleneck. Inverted bottleneck is like you have something much larger in the middle and smaller on both ends. So this becomes the bottleneck, right? So bottleneck layer, inverted bottleneck layer, this middle part is 6 times larger than this previous and next layer. Everyone get the point? Okay, good. All right, so having talked about the challenges of TinyML and the challenges of the peak memory, let's dive deep into how do we solve these challenges by tiny neural network design. So we'll describe 2 pieces of work from our group. One is MCUNet, published in 2020. The other is in MCUNet v2 in 2021. Both were highlighted by MIT News. So existing work, okay, either focus on searching the neural network model, assuming we have a fixed library, right? So such as proxyless NAS, MNASNet, which we covered in the NAS lecture before, right? Assuming a fixed hardware, fixed library, we want to just tune the neural network architectures. Another kind of work focusing on changing the library, okay, making innovations by writing a more efficient library, such as TVM, to tune the kernels, tune the library, right? So given such memory constraint on microcontroller, we find it not enough to do either. But we should open the design space to design both the neural network architecture ourselves and also the inference engine, which is the inference library on the microcontroller on ourselves. Okay? So which opens up a larger design space and allow us to do a better trade-off, right? So this TinyNAS stands for Tiny Neural Architecture Search, okay? Provide efficient neural network architecture. And this TinyEngine provides an efficient compiler and runtime, okay? So they work coherently with each other. So first, using TinyNAS, we design and auto-optimize this neural network structure, which is the focus on today's lecture. And for TinyEngine, we will introduce that in lecture 17. Okay? Both TinyNAS and TinyEngine are open sourced on GitHub, so you're very welcome to use them for your course project as well as your research projects. So we talk about this big picture of neural architecture search, right? So rather than using human expertise to manually design the neural network architecture, okay? So we want to use this computational resource to assist conventional human design, right? To use a lot of GPU resources to do this automatic architecture search. And we described that in order to do NAS, we need to have the right search space rather than searching across the entire forest. You want to narrow down the search space if you want to find your friend who got lost, right? So the quality of the search space actually determines the performance of the model, right? So the first step is to narrow down from this full network search space to some subspaces. Okay, we want to pick a good search space to begin with. So there are several options, right? What determines to find a good design space? Okay, so option one is to reuse the prior design spaces that are carefully designed by other teams, right? For example, MNAS space, MobileNet v3 space, once for all space. However, those search spaces are actually designed for mobile devices, like mobile phones, which has much larger computational capability than such a microcontroller, right? So this option is not quite viable because even the smallest subnetwork, like the smallest subnetwork in this search space, still cannot fit the hardware resource. Okay? For example, a microcontroller has 300 kilobytes versus a mobile phone has 4 gigabytes of memory. So it's hard to reuse the mobile search space. Therefore, we want to pick a customized search space for this IoT device. And how do we do that? So we can specific scale the MobileNet-like search space, okay, by using different resolution and with multipliers. So this resolution and width multiplier determines a sub search space. Okay? For example, the original search space for mobile phone, people widely use this resolution of 224. If you go to ImageNet, most of the resolution is 224. And the width multiplier is 1.0. Okay? But this is not the case for microcontrollers. For GPU, we can have a larger resolution, larger width multiplier, but what about for these microcontrollers, right? And also, they can have completely different memory resource from 256 kilobyte all the way to 512 kilobyte. So we want to first design the design space and optimize the design space, and then perform neural architecture search. And here are the design knobs that we want to tune, right? So the resolution and width multiplier we mentioned, that defines a search space. And within the search space, we want to further search this kernel size, okay, 3, 5, 7, okay, and the expansion ratio, and also the number of blocks, the depth per stage. So let's discuss how do we design a good search space. Okay, so we don't have to look at the figure yet, but a key principle here is that computation is cheap, memory is expensive, right? We want to perform more computation given the same amount of memory footprint, right? So here the heuristic becomes given the same memory constraint, right? A good design space is more likely to achieve higher flops, okay, under the same memory constraint. So here we plotted several design spaces. Width and resolution, the width ranges from 0.3 to 0.7. Resolution ranges from like 96 all the way to 160. So we plotted a lot of combinations of such width and also the resolution pairs. Okay, and then we just analyze what is the number of flops that can fit, right? So this doesn't require any training. We just calculate the flops analytically. For this red design space, okay, which is width of 0.5, resolution of 144, okay, we can see pretty much all the models, okay, all the models are larger than 41 million flops in this design space, which is pretty good. However, a bad design space like this, all the models has only 28 million flops, okay, in this design space. And for the red design space, 20% of the models are larger than this 50.3 million flops, okay, which is larger than this black design space, where 20% of the models are larger than 32 million flops. So by being able to fit more flops means that we can have more operations, more capacity in this model, right? It's more likely to achieve higher accuracy, right? So larger flops indicates larger model capacity, more likely to achieve higher accuracy, right? So the condition is that they are given the same memory constraint. So we first should fit this model, right? Of course, larger flops also means longer latency, right? But computation is cheaper compared with memory footprint. These two design spaces, these two designs can have the same all falls under the same memory constraint. Okay. All right. So using that heuristic, we try to find what happens when we have different size of the SRAM, okay, versus different size of the flash. Okay. So on the top, we plotted the scenario for between this flash and also the SRAM, okay, for the width multiplier. Okay, on the bottom we plotted that for the resolution. Okay, width multiplier ranges from 0.3 all the way to 0.9. Okay, the resolution ranges from like 80 by 80 all the way to like 208 by 208. Okay, so as the flash increases, but given the same amount of SRAM, so we are increasing the flash from 512 kilobyte all the way to 2 megabyte. So what happens to the model design? Let's brainstorm a little bit. What happens to the model design if we increase the number of flash? How should we change the width multiplier and also the resolution? This is the width multiplier. The green part is the resolution. Right, the width multiplier is dependent on the flash, right? Since we have larger flash, means we can fit a larger model, right? Therefore, we want to have more channels, right? So we increase the channel width multiplier from 0.4 to 0.8, right? But increasing the number of channels also means we will require larger amount of SRAM if other things stay the same. However, we have the same SRAM, therefore we can only decrease the resolution so that we can still fit within the same amount of SRAM, right? Okay, so what about the other direction? We increase the SRAM, okay, increase the SRAM, but we keep the same amount of flash. What happens for the width multiplier and for the resolution? The answer is there, but I'll give you some time to think about it. So we can see the SRAM didn't change much, right? 0.4, 0.3, 0.4, 0.4. here 0.8, 0.9, right? Because we have the same amount of flash, meaning that the weight is the same. So which shouldn't change the width multiplier because the weight should stay the same. However, we have more SRAM. Therefore, we can hold a much larger resolution, right? So the resolution becomes bigger from 112 to 208, right? From 80 to 144. Okay. So this gives you a good exercise about seeing the trade-off between how do we adjust the width multiplier on the top versus the resolution on the bottom, given different resource constraints on SRAM and also for the flash, right? This might also be helpful for those of you who want to play with new technologies, right? Some of the technology may have some read-only, non-volatile versus volatile, right? So this gives you an idea when you're designing the neural network architectures to fit different memory constraints. Okay. So here's the answer if you want to go back and redigest it. Okay. Everyone on the same page? Yeah,
Would
question?
the resolution be in the volatile memory then? Or would it all be in
Oh, so the weight have to be in the non-volatile memory. You have to keep the weight across different inferences. Yeah. And for the resolution for the input image, the activation, you can put it in the volatile, like SRAM, since it's gone away from layer I to layer I+1. All right, so after designing the search space, then we can perform neural architecture search. So we can use the once for all neural architecture search approach, right? So we first train this SuperNet. Each time we sample different subnetworks, either random sample or using this progressive shrinking method. And then we sample them, we jointly fine tune multiple subnetworks. They share the weights, right? Like different components, they share the weight with each other. And those smaller child networks are actually nested in larger ones because they share the weight. So we just need to keep one largest copy. Then we can have multiple smaller copies to fit different microcontrollers constraints. Okay, so the neural architecture search model is on the right-hand side. Compared with the hand-designed models, MobileNet V2 is on the left. We can find, actually, this is plot of the peak memory for different stages, right? For manually designed model, actually the largest model versus the average model differs by 2.2x. So this is really a dominating stage. But for TinyNAS, this number is only 1.6 times differ, right? Meaning that the TinyNAS designed model has a better utilization, right? A less aggressive dominating stage like the human designed models versus this one is flatter. And then we'll talk about other techniques to even get rid of such dominating activations. So here I'm going to show some results. Okay, so MCUNet, this is the latency, and on the right-hand side is the peak SRAM usage. So several baselines, MobileNet V2 from Google, Proxyless NAS, which we described before, and this is our prior result in 2019 in the Low Power Computer Vision Challenge. Okay, so by designing this TinyNAS, on this visual wake-worth data set, we can achieve like 2.4 times faster model, okay, requiring 3.7 smaller amount of SRAM while maintaining the same accuracy. Okay, so just now we briefly talk about this memory bottleneck, right? So for example, this block have a huge amount of memory, okay, which dominated all the layers. So even if these layers are all smaller than what we have as a memory budget, these layers are very bad. Okay? So these kind of stages cannot fit this 256 kilobyte of memory constraint on microcontroller, right? Only these models can fit, and they differ by as much as 8 times. Okay, then how do we find ways to conquer such problem for these dominating activations? Right? So let's continue our discussion about how do we conquer such memory bottleneck for several dominating layers. Okay, so conventionally, when we are doing inference, we do this layer by layer inference, right? So we do layer 1, layer 2, right? So when we are doing inference, we have to keep both the input activation and output activation in the memory when we are processing that layer, right? So the largest memory footprint is equal to the max of this sum versus this sum. Okay? Given the first couple of stages where we have this large resolution, such peak memory could be pretty large, right? But for later layers, as the resolution gets pooled, the footprint will be smaller. That's why those peak memory happens in the first couple of stages, right? So we propose kind of a new idea, which is patch-based inference, right? Rather than processing the entire H by W, we want to process maybe only a quarter of that, right? Imagine you are eating a pizza. A pizza is too big, but you just want to have a quarter of the pizza at a time. So this is the peak memory that is needed. And after computing that, we have this partial solution, right? We only have this partial output. So we have to allocate the whole memory to store these partial outputs. But luckily, after the pooling layer, the memory footprint becomes much smaller, right? Therefore, we can have the opportunity to shrink the peak memory. This is an example of dividing that by two by two chunks. Okay? We can also divide it by 3 by 3 patches. Right? In that case, the peak memory would be even smaller. Very simple idea. So the reason we can use this is thanks to the fact that we have these pooling layers, right? So at some point, we have to store the entire feature map, the entire H and W. Due to several stages of pooling, that H and W become smaller. So this is before and this is after this patch-based inference, right? So this is before patch-based inference, the peak memory could be as big as 1,400 kilobytes, right? And after this patch-based inference, it's something below 280, right? So we successfully alleviated this peak memory issue. So evaluated on many different benchmarks, right? MobileNV2, redistributed FBNet, MCUNet. This is the peak memory for conventional per layer based inference, right? And this one is using a 2 by 2 patch, okay? And this is using this 3 by 3 patch. So theoretically, 3 by 3 patch save you 9 times the memory. But due to you have to store the last layer, the actual saving is smaller, ranges from 4 times to 5.9 times. Okay. So is that the whole solution? Actually, there is a issue with such patch-based inference. So imagine we are doing this threaded convolution. So this convolution, have this receptive field, right? So after one layer, this is the receptive field, becomes amplified by 2x, since we have a thread of 2. After another layer, since due to a 3 by 3 convolution, each layer we expand the receptive field by 2 pixels, right? So we have this halo region, which is the overlap between different pixels, right? So running such patch-based inference will lead to this overhead of computing this halo twice, right? So this spatial overlapping gets larger as the receptive field grows, leading to larger computation overhead. So how much is the overhead? It can be as large as 10%. Okay? So for MobileNV2, it increased the median max from 300 to 330 median max. Okay, so using such patch-based inference. So all is due to the much larger receptive field. So naturally, we can think about a technique to redistribute the receptive field, right? So here we move one of the layers from the first couple of stages to the later couple of stages, right? So the total receptive field keeps the same, right? But here we replace this 3x3 count with this 1x1 count, which doesn't expand the receptive field. So by tuning this neural network model, okay, by changing the neural network model without changing the inference library, we can reduce this overhead. Okay? So the final flops is going back to 301 millimax. So same performance on image classification, object detection with negligible overhead. And finally, we jointly optimize the neural network architecture and also the inference scheduling. Okay, number of layers, number of channels, the kernel size, as we did before in the once-for-all technique. And also here we tune the inference scheduling, including the number of patches. Okay, how many layers are we using the patch-based inference versus per layer-based inference? Other knobs are the same from TinyEngine. Okay, so this is the result on the visual wake-words dataset. Visual wake-words is basically detecting whether there's person or there's no person in the room. Okay, so that you can turn on the appliance or turn off the appliance or the lights or whatever you have, the AC, etc., by detecting whether there's a person or no person. Very widely used TinyML application. You can use such dataset in your final project, which can fit only 30 kilobytes of SRAM. So if you have Arduino, it's very likely you can fit such a tight memory constraint. This is a mobile MV tool plus Google's TensorFlow Lite, okay? TensorFlow Lite Micro. And this is our result in 2019, right? In 2019, we can achieve 256 kilobytes of SRAM with 88% top-line accuracy, right? So 88%, we are having the correct prediction. This is our 2020 result, MCUNet. Okay, so MCUNet, we reduced the memory from 256 to only 128 kilobytes, but with even higher accuracy. Now we have 90% accuracy. So the second version of MCUNet v2 actually further pushed that by 4 times. Okay, so still 90% accuracy, but require only 30 kilobytes of SRAM. Okay, and this is showing the memory reduction from 120 to 30 kilobytes. And also, this is showing on this STM32F412 microcontroller, okay, with 256 kilobytes of SRAM. The accuracy improvement from MobileNavi2, which only 49% top-line accuracy, to about 64 top-line accuracy with MCUNet-v2. This is another constraint, slightly better device. This is Cortex M4. This is Cortex M7 with slightly larger memory. Okay. And on the right-hand side is showing the detection accuracy, right? So detection is a different task. We want to not only classify what it is, but also draw the bounding box for each object, right? So here, from MobileNavi2 to MCUNet-v2, 16.9% improve of top-line accuracy. So from classification to detection, we can find that by smarter model design, the improvement on detection is much higher, much larger than classification, right? Because so MCUNet-v2, it can alleviate this large activation issue so that we can fit a larger resolution, right? And for detection tasks, the resolution matters a lot. Otherwise, those small objects will be completely lost under small resolution, right? That's why such detection tasks we can have a much more significant accuracy improvement compared with classification. And also, detection is actually a very widely used application, much widely used than classification. So I highly recommend to try that for your final project. Okay, so here we want to go a deep dissection to understand why this MCUNet v2 architecture works quite well. So here is the architecture for MCUNet v2. It has different colors. Okay, so for example, this dark red color indicates the kernel size is 7 by 7, versus this one is 5 by 5, orange, versus the yellow one is smaller kernel, 3 by 3 kernel. Okay, and the legend is denoted by the expansion ratio, okay, indicating the number of channels, expansion ratio of 4, 4, 4, etc. And this is wider, right? Expansion ratio of 6. And then followed by kernel size times kernel size, right? 7 by 7 layer, 3 by 3 layer, etc. And we can find that the kernel size in those per patch based stage is very small due to we want to reduce the spatial overlapping, right? So this per patch based inference, we want to reduce the receptive fields overlapping in order to reduce the unnecessary computation. So here they are using smaller kernels, even 1 by 1 kernel. Secondly, this expansion ratio in the middle stage is small to reduce the peak memory, right? So we can find the expansion ratio is only 4 in the first couple of stages, since here we still have pretty big resolution until over here, right? So in order to reduce peak memory, they chose to have a pretty middle size, like only 4 for the expansion ratio. But in the later stage, they begin to use much larger expansion ratio, since the resolution is already pretty small. So then it makes sense to have a larger expansion ratio in this inverted bottleneck layer, right? So here we can have a much larger expansion ratio without hurting the peak memory, since the resolution is already really small in the late stage. Okay, and MCUNet v2 can hold a much larger resolution, 160 by 160, compared with MCUNet, the first version of MCUNet. That's why it performs quite good on those resolution-sensitive tasks, for example, detection tasks. Okay? So all these rules, we never taught the neural net designer to do this, right? But by using this TinyNAS, tiny neural architecture search, the design model really makes sense if you want to dissect all the design details. Very smart. And we don't have to train a designer to do that, but just push the button, let the GPU do the search, and then finalize, it can return as the model that fit such constraints. All right, so I'm going to introduce a couple of other works, okay, targeting this TinyML and tiny model design. Okay, so far we talked about using CNNs for these vision models, right? So what about combining CNN with some RNNs? Okay, so this work is called RNN pool, right? Focusing on reducing the peak memory, okay, for the first couple of stages where the resolution is large, right? So using this method, it can aggressively pool the model by 4 times. By using this RNN layer, okay, RNN has like timestamp of 4 timestamps. Okay, so pass it through a recurrent neural network to get a final answer. Similarly for other 4 rows, and then it passes through a second recurrent neural nets, in both directions to get the final result. Okay, and then it does the same process in the other direction. Okay, in the vertical dimension, pass every 4 elements into a recurrent neural net, and then pass the result to a bidirectional neural net in both directions. Okay, and they concatenate the output of all the passes and becomes the final output. So this final output is really due to the result of these 16 pixels. Okay, so it quickly pulls the resolution from the original resolution to that divided by 4. Okay, so it very quickly shrinks the resolution. So as a result, rather than having such a lot of large resolution activation bottlenecks, that gets replaced with this RNN pool layer. Okay, so quickly reduce the resolution from 112 to 28. Okay, 4 times smaller using this RNN pool layer. So we no longer have that memory bottleneck. So very interesting idea to replace a sequence of blocks here, of convolution blocks with recurrent neural nets. Another work called MicroNets. Okay, so the key idea here is how to estimate those hardware costs of the neural network, including the latency, the energy, right? So the peak memory is easy to analyze, right? We can easily calculate them for a given model since that is static, it's not hardware dependent. And from this paper is finding that actually the latency, right, okay, as a matter of the operation count, the median ops, okay, is actually the latency is actually linear to the number of computation flops, okay, computation ops, okay, assuming that we are sampling from the same supernet. Okay, so they learned both, tested both the image backbone in blue and also this audio backbone in orange. Okay, and find that the end-to-end latency on these two microcontrollers are quite linear with respect to the number of computation ops. So the subnets sampled from the same supernet, we can actually assume this linear relationship between latency and flops. What about energy? People care about energy since we want to, most of these IoT devices are battery powered, right? So given the same assumption where just sample from the same subnet, actually the energy consumption in this paper they find is also linear to the median ops, okay, since they are from the same design space, both for the vision model and also for the audio model. So this really gives the insight, how do we estimate the latency and estimate even the energy without physically testing it. The precondition is that they are sampled from the same design space, the same supernet. All right, so let's conclude the tiny neural net design part. Okay, so we've mostly described how to reduce the peak memory. Okay, now let's cover a few applications, including tiny vision, tiny audio, and also tiny time series and anomaly detection. So let's start with tiny image classification. So with techniques like MCUNet, we can do not only such easy toy application like classifying apples, oranges, and bananas, right? But we can actually do such real-life applications on these large-scale data sets, even match the accuracy up to 70%, okay, on ImageNet data set. So that really unlock a lot of cool applications. So this is the top one ImageNet accuracy we can achieve on many different microcontrollers. Okay, so conventional approach, Google's MobileNet V2 plus ARM CM6NN can achieve only about 54% top line accuracy on ImageNet, which is even below AlexNet. But with MCUNet, we can achieve more than 70% top line ImageNet accuracy, almost to the level of Ryzen 18 and MobileNet V1, right? So this is a big breakthrough. And also it can enable several applications like visual wake words, detecting if there's no person, the appliance can be idle. Once the camera detects a person, then we can do something, right? And if there's no person, the appliance can continue go idle. It's pretty much like the vision counterpart of this Hey Siri or OK Google, right? Rather than speech triggered, this is vision triggered. And this is a demo that we have in building 36. We have a microcontroller attached to the elevator. If it sees a person, it will turn red. If there's no person, let's watch again. Person, there's red. If no person or people walk away, it'll be green, right? To detect whether there is person in the room. So that is a basically classification task. We can also do object detection tasks, right? So object detection not only have to predict what it is, but also where it is, right? So it is actually very sensitive to resolution. As we decrease the resolution, we can find the classification model on ImageNet, the accuracy doesn't drop significantly. But for detection, the accuracy actually drops very significantly as we reduce the resolution, right? Since in object detection, if you have a small object, if the resolution is too low, you cannot detect those small objects. So it's very crucial to have a large resolution. But it's not free lunch, right? Large resolution means you want to have a larger peak memory, right? Which is limited on microcontrollers. That's why we need techniques like MCUNet to reduce the peak memory so that we can enable this detection to draw these bounding boxes locally on these microcontrollers, right? So here we are doing phase and mask detection, not only single person, but also multiple person, mask, no mask, okay? And on the right-hand side is person detection, people walking by, people sitting there, can all be accurately detected. So this is really the benefit from such patch-based method, allow a larger input resolution and saves the peak memory footprint. Here are more examples comparing the RNN pool and also the MCUNet v2. Since MCUNet v2 can hold larger resolution, then there's a lot less mispredictions, like mispredicting the hand as a face, right? Versus having a one less prediction for the side of the face, right? Versus here missing a prediction versus a correct prediction. So large resolution matters. We can even actually do on-device training. For example, this is on the microcontroller. We have two buttons, one button here and also a blue and also a green button. We can push the button as the camera is facing to different objects. Okay? We can push it, but just a couple of times, and then it can learn to backpropagation, can learn the new objects. And then without any pushing the button, it can turn red for the first class and turn green for the second class automatically. Question?
Is that what TinyTL?
So not only TinyTL only proposes by its only update. So this technique is our new publication in Europe 22 called on-device training under 256 kilobyte of memory, which introduced a new idea, sparse layer, sparse tensor update, and also use 8-bit quantization to do quantize the training. So we will leave it in future lecture. We'll cover that in the on-device training, on-device learning lecture. So far, we covered everything is about inference, right? So in the second half of the semester, we are also going to talk about training, both distributed training and also on-device training from next week. All right, then let's switch gear from vision to audio applications. So lots of speech recognition applications, text-to-speech, machine translation, a lot of speech or natural language related applications. So the basic idea, the basic flow of processing the speech signal is actually having this, say the speech command is actually lasting a time t, the total length is L, but we chop it into several small windows of small l, okay, overlap by s. So all together we have this number of frames, big L subtracted by the small l divided by s plus 1. Okay, this amount of frames. And for each frame, people usually convert that into the frequency domain, okay, the strength of different frequencies at different time stamp. Okay? And then the popular approach is to run neural net, treat this as an image, okay, and run convolution on this frequency domain representation, okay, and finally give the prediction of each speech command. Okay, classification problem. And people have found that such CNN-based method by treating the representation as an image and run convolution on that is usually have a lower error rate compared with just running DNNs without considering time information. So here we show that it's deployable, it's doable to use MCUNet for such for such speech command recognition tasks. Okay, so this is Google speech command dataset. Okay, GSC. We can have like 2.8 times faster inference compared with using MobileME2. Okay, since after such conversion, this is just treated as an image. So all the techniques that we talk about for convolution neural nets can be applied here to deal with the speech data. And on the right-hand side is showing the memory footprint, actually 4 times smaller compared with using the MobileME tool by switching to MCUNet. And finally, we'll cover a popular time series and anomaly detection task that is quite widely used in smart factories. So there are many application domains, like detect whether the wire is abnormal, right? Detect whether a capsule has some broken parts, right? For example, if you use manual inspection, that's going to take a lot of efforts. And whether there's some broken parts in the nuts or in the bolts, okay? And also detecting whether abuse, arson, accident, explosion, robbery, etc. Right? And these are vision-based methods. There are also other methods that are based on time series, right? Like temperature, like accelerometer, etc. So the basic idea for anomaly detection is using these autoencoders, okay, which is a neural network that encodes the input into a hidden space, into a low-dimensional code vector. Okay? And by you passing that through a couple of other FC layers, which is called a decoder, and we want to fully reconstruct the input to the output, okay, and try to match the input with the output. Since for anomaly detection, we usually only have the normal data. We don't have the abnormal data. So this autoencoder is able to encode the distribution if it falls within the same distribution as the normal data. But if abnormal data comes here, this autoencoder cannot reconstruct that data. So if we calculate the difference between input and output, we can figure out whether this is normal data versus abnormal data. Okay, so this is purely unsupervised. We don't have label. We just have the normal data where we don't have the labeled abnormal data. Okay. So here is an example of reconstructing the input, right? And by seeing the reconstruction error, if it is too big, then we will predict this is not falling under the same distribution as the normal data. Then we classify that as abnormal data. And this autoencoder is actually lossy, right? It cannot be exactly recomputed. So even for the normal input, we should expect the error not to be completely zero, but a smaller number, right? And here is a demo for anomaly detection we have in our lab. So this is a fan, right? And we have here is a light right here. If you're poking into the fan, this yellow light will turn on, right? And will disappear. So this light is showing something abnormal happens. So this yellow light up again. So this microcontroller has an accelerometer attached to that. So if you rotate it, if you poke that, so it will be classified as abnormal, right? So the resource constraint is our ARM Cortex M4 microcontroller, right? 256 kilobytes of SRAM, 1 megabyte of flash. So there are several commonly used anomaly detection approaches, including k-means, right? Autoencoders, and also Gaussian mixture models. So feel free to use this board to do your final project, but we don't want to restrict the final project. Just give you some idea. All right, so in summary, we talk about this TinyML, both the challenges, the solution, and also several applications. Okay, so we will have this paper presentation in the next lecture, okay, 1 to 3 students. And from the next week, we will switch gear from inference to talk about training. Okay, and we'll introduce techniques to make training faster, both on the cloud and also on edge devices. So we are already in the middle part of the semester. I hope you are enjoying the class. We'll be taking the feedback if you want to send us an email, right? And so far we talk about this training inference part, and then we're going to cover the training part and system support, and also these application-specific optimizations, including some of the most hot topics in autonomous driving, point cloud, okay, video understanding, and GAN models, okay, and also transformers and natural language processing, followed by several lectures on efficient quantum machine learning and final project presentation. Okay, so hope you enjoy the lecture. We are happy to take feedbacks, and today we have actual office hours for you to help you guide you through lab 2 if you have any questions. Okay, that's the end for today's lecture.